Affinity series, and we have been having some excellent talks. You can hear me, right? Okay, good. And today is, with no exception, with Dr. Kehl joining us. So let's give a quick introduction to the PHI. We hear from leaders in the field and discuss trends in artificial intelligence with healthcare, and we bring together AI researchers in a variety of fields to try to solve problems that were not solvable 4 or 5 years ago. So the format of the talks are roughly 30 to 40 minutes with interactive QA at the end, and we always have a lively discussion. So if you have any input to myself or Dr. Sadowski, my co-chair on this group, please just email us directly. We're being hosted by the University of Hawaii Cancer Center here on the Kaka'ako campus in Honolulu that we share with the Johnny Burns Medical School. And the Artificial Intelligence Precision Health Institute really sponsors these talks and also sponsors students to work on problems in healthcare. Also, part of the UH system is the Hawaii Data Science Institute, which also sponsors students with fellowships to bring them into machine learning and deep learning. We have a very generous speaker compensation, which is a beer stein. And here's just a few of our previous speakers showing off their steins. The paper of the month is from Dr. Kehl, and it's entitled Shareable Artificial Intelligence to Extract Cancer Outcomes from EHR for Precision Oncology Research. If you follow me on LinkedIn, I posted a link to this, and hopefully some of you guys had a chance to read it before his talk, so we can better enjoy what he has to say. So just as a matter of introduction, excuse me one second here. Dr. Kehl is from the Dana-Farber Cancer Institute. He is a working thoracic medical oncologist, and his work focuses on developing methods that leverage observational and electronic health records for cancer research, which is really, I think, a great ally, because many times we have physicians that are that we work with, but very few that go deep. And so I think Dr. Kehl is one of those physicians that's deep in it. So we appreciate him being here today and to share what he has to say.
Great. Thanks so much for having me. Yeah. Okay. So thanks again for having me. I'll be discussing some of our work around shareable AI to try to extract cancer outcomes and increasingly other data elements from electronic health records to drive precision oncology research. And this will cover that paper as was kindly pointed out, and also some kind of ongoing thinking about working towards more ideal methods to think about this challenge. So as folks likely know, historically at least, obtaining cancer outcomes from EHRs at scale has been a barrier to certain types of cancer care delivery, research, and observational research. Just understanding whether a cancer grew or shrank in response to a treatment, which of course for oncologists is a major piece of what we monitor, has historically required either collaboration with radiologists to do formal annotation of imaging or manual review of charts to get these data, and that obviously has challenges when it comes to scalability. So potentially AI could help us overcome this challenge, but privacy concerns often preclude sharing AI models that have been trained on raw EHR data that are identified. What we explored in this paper was whether a quote teacher student or distillation framework can be used to train more portable AI models to extract outcomes from EHR text reports. But as I'll review a bit, I think we still need methods and thinking around how to quantify and qualify privacy risks and deploy shareable AI with patient privacy protections. So that's the broad overall summary. Kind of dive in a little more depth. So, as I alluded to already, I should note as a disclosure, many of these images were AI generated. Um, uh, as I noted, cancer outcomes data in routine clinical care are usually recorded essentially just in the unstructured text of an imaging report or a clinical note in the electronic health record. But many of our research questions require these outcomes data, and there's too much of it to do manual chart review at scale to annotate records for, say, thousands or tens of thousands of patients. Over the last several years, we and others have trained models on our own institutional data sets to do, for example, text classification tasks, read an imaging report and indicate or predict whether there's progression or growth of cancer on that report. And we had shown in, for example, this publication from a few years ago now that this yields outcomes that are clearly capturing the signal of when the cancer's getting worse. We looked at whether they're associated with survival in the ways that you would expect, and they were and treatment change. This was an example of an analysis we did where we used data that were extracted from imaging reports using these AI models, looking for progression of disease, and applied those to define progression events to ask here an example question. In this case, what was the association between tumor mutation burden and progression-free survival on palliative intent immunotherapy across cancer types, where the progression events now are essentially AI extracted. And we saw associations in the directions you would expect. Now, across cancer types, TMB is a more or less effective biomarker, depending on the disease context clinically. But this just demonstrated that with this sort of tool, one can ask a question about a cohort on the order of thousands of patients much more quickly than one can do if you're needing to manually review the records to find the progression events. Our colleagues at Memorial Sloan Kettering Cancer Center deployed a even more extensive version of this type of strategy in their MSK Cord paper, where they took their clinicogenomic cohort from Memorial Sloan Kettering and applied these methods to extract outcomes as well as a number of the features and exposure variables, and essentially made a subset of those data publicly available on CBio portal, which, as you may know, is a tool you can use to visualize cancer genomic and clinicogenomic data. So this type of model can be useful. But as I alluded to, although we've been able to train these types of models and apply them at single institutions, their utility and generalizability more broadly have been limited by restrictions on sharing models that were trained on PHI, protected health information. There are risks that models trained on PHI can encode or memorize that information in various ways that I'll get to shortly. The concept of federated learning has been proposed as one solution to this type of concern. In federated learning, as folks know, the training data stay at home in source institutions, but a model is jointly shared on those data by sharing just the model weights or weight updates in sort of a simultaneous training process. But that does not do anything really to inherently mitigate this concern that the models themselves might bake in some of the training data. So what are the potential privacy risks when models are trained on PHI? Uh, Probably the most obvious is just simple data regeneration. If a generative model, particularly a large language model or a language model in general, is trained on clinical text data, this can sort of obviously happen. I plugged into Chat GPT a few weeks ago, finished this paragraph. It was the best of times, and the response clearly indicated that it had memorized this quote. I mean, its internal thinking process was like, am I allowed to reveal this information? Oh, it's public domain, so I can go ahead. But when I've tried training models on clinical text, it's pretty clear that generative models can learn to directly regenerate training data under certain circumstances. There are other forms of attacks or risks that folks worry about. One is a model inversion attack, where given access to a model's um, weights or labels or outputs, it can be possible to regenerate training data by sort of looking at the activation patterns of the model given some input, yielding in this case a sort of modest facsimile of a image regeneration from training data. And then there's this other form of attack or vulnerability that I've been thinking more about, since I think it's more directly relevant to the sort of classification tasks that I've been thinking about, at least with respect to the the task of getting outcomes out of the electronic health record. And this is a concept called a membership inference attack. And I know I'm probably speaking with audiences that are more familiar with all of this than I am. I've sort of been diving into it out of necessity. But a membership inference attack essentially would consist of um, trying to figure out, for example, if I know something about Mr. Smith, um, I have some data on him in some form. Can I figure out whether he was included in the training data set for some model? So, for example, if I have a model out of a cancer center, uh, can I figure out that Mr. Smith was in a model trained at that cancer center, which then would tell me that Mr. Smith was treated for cancer at that center? Um, this is a diagram of how that works. There are different versions of this type of attack depending on whether the nefarious actor has access to the raw model weights or just the outputs of the model. Um, but this is something that even just classification models can, at least in theory, be vulnerable to. Uh, Diving then even deeper and out of what I could justify as at all my formal expertise, one approach to thinking about these privacy risks is this differential privacy concept, which loosely, as I'm sure folks know, tries to measure and, in some sense, minimize or quantify the probability that including a specific patient or observation in a training data set significantly changes the output of models trained on that data set. Since, in some sense, a fully private model should not yield any information about whether a particular patient or observation was included in model training. Fine. There are parameters that are used to quantify the extent of privacy protection baked into any model or really any sort of data gathering or generation process. And this has been my best attempt to understand these metrics. So there's this epsilon parameter, which the lower it is, the less of a shift in model outputs we tolerate before declaring that a given patient's data is not private if including in training. And this delta parameter, which essentially specifies how much tolerance we have to outlier events or model outputs, um, uh, such that the lower it is, the less tolerant we are of outlier cases where the probability of some model output is very low. These are some formal, so this is from the Wikipedia page. It helped me understand what epsilon stands for on differential privacy. This is a more digestible publication, I thought, for uh, sort of directed at privacy officers and folks who may not be deep in differential privacy and cryptography and stuff, for trying to understand how to clinically or just in general sort of in domain applications apply this concept of differential privacy. I think one thing to be aware of with differential privacy is that there is a trade-off, pretty universally recognized between the extent of privacy protection of a model and how well that model performs. So this was a very recent, preprint publication by Google, where they trained a version of one of their large language models, Gemma, that they called Vault Gemma, by baking in differential privacy guarantees to the training process, such that and they showed that any one observation, as long as it was only sort of a single observation, wasn't getting memorized by this version of the Gemma large language model. But then these are the performance metrics of this model, and you can see how much lower these numerical performance metrics are for this Vault Gemma model than for the versions of the models that they had trained that did not bake in the differential privacy protection process, and this even included GPT-2 from several years ago now. So, one of the challenges I've been starting to try to wrestle with is how do we make sense of this differential privacy concept and interpret it in the clinical or healthcare research or operational setting. For example, how do we translate this differential privacy concept into legal language for privacy offices whose job description is not usually historically included trying to assess the privacy risk posed by some specific new AI model. Another challenge is there's no standard way to empirically check how differentially private, at least according to these parameters, according to these parameters, a model is once it's been trained. You can train a model with techniques that try to bake in differential privacy guarantees, but it's my understanding is it's harder to go back and empirically check that after it's done. I think another question in my mind is sort of how much, from a common sense perspective, in a way, does it make to worry about this membership inference attack kind of vulnerability to AI models, since these by definition require that the nefarious actor already has some fairly granular information about a patient in order to then use it to try to find out if the patient was included for training in a model. And I don't know, often to me, it sort of feels like that framing means the sort of cat is out of the bag in some sense already by the time the attacker is kind of coming in to try this. But it's a type of vulnerability that people do think about and worry about, and we certainly want to protect patient privacy. So uh, I'll now describe the paper that was circulated there, which was my initial foray into sort of shareable AI models. I'll say up front, I did this in a way that was sort of newer and I thought interesting at the time. I don't think I would try this as such at home, because there's been even more recent work showing that it's not as privacy protecting inherently as you might hope. I think in our case, we sort of can show empirically that any risks seem quite low to this infrastructure, but I'll talk about that in a little more detail. So the idea here was, can we use a teacher-student framework, which is also essentially a model distillation approach to train models that are designed to get information out of the electronic health record about outcomes. This is just a depiction of this general concept of distillation or teacher models teaching student models. So what we undertook was an exercise towards trying to develop shareable outcome extraction models where we trained teacher models on, in our case, Dana-Farber data to predict human annotations of outcomes from imaging reports and oncologist notes at our site. And we use data for this that I'll describe shortly. Then used these teacher models to label text notes from the MIMIC dataset, which I imagine folks are familiar with. It's a corpus of structured and unstructured EHR data from an ICU setting, and the four patients who at some point spent some time in an ICU. Once we had these teacher labels, we then trained student models. So sort of uh, new naive versions of the same models to predict now the teacher labels that had been generated and applied to the public data set. And then we did get IRB approval and buy-in from our data office, at least at the time, to then share these student models with Memorial Sloan Kettering Cancer Center, which had some similarly labeled data so they could evaluate it on their own data sets. The data set that we used for training and validation came from our participation in a clinicogenomic annotation project as part of AACR, American Association for Cancer Research Project GENIE, which collects large-scale genomic panel sequencing data on tumors from academic institutions internationally. On a subset of these cases, we had performed granular manual annotation of individual imaging reports and oncologist progress notes from along the disease trajectory, and those served as our labels for this project. These are the types of labels that were associated with individual imaging reports here. This included basically, is the radiologist describing active cancer on this scan? If so, is it progressing or worsening? Is it responding or improving? And has it spread to a select list of metastatic sites of organs that it has involved? Also had labels that had been generated for oncologist notes, essentially just trying to capture, uh, as of the time of this note, was the oncologist saying that there's active cancer today? If so, was it progressing or worsening, or was it responding or improving? And of course, sometimes there's active cancer that's neither progressing nor responding, but stable or experiencing a mixed response. As I alluded to, we used a, I guess, semi-public data set, the MIMIC data set, for labeling and then student training. We used two types of notes. For the imaging report training exercise, we used imaging reports. I tried to restrict to ones that appeared in some way cancer relevant for this cohort, so included the terms cancer or restaging or malignancy, malignant, and were of the types of scans that we usually do to reassess a patient's burden of cancer. And then there are no, at least to my knowledge, there were no at the time, progress notes from the outpatient setting in the MIMIC data set. So we actually used just discharge summaries, and to try to filter for a little more domain relevance, did a similar restriction to those that had some cancer relevant terms and still wound up with pretty large size student training data sets. These models themselves were pretty straightforward text classification models. They were based on the BERT architecture from 2018, which is a masked language model architecture, sort of base model on which one can train classification heads. In this case, these were multitask models. So one model each for imaging reports and oncologist notes. For imaging reports, this was essentially a 10-headed model, simultaneously predicting each of those labels that I mentioned had been assigned to the imaging reports. And then for oncologist notes, it was a 3-headed model predicting, is there any cancer? Is it progressing? Is it responding? This was a diagram of the overall training and evaluation strategy here. So we used documents from Dana-Farber that had been labeled as training, tuning, and test sets. These were split at the patient level into these three subgroups. We trained this teacher model with Dana-Farber, evaluated its performance on the test set from Dana-Farber, and then we used this teacher model to label those mimic clinical documents that I alluded to. Then a student model was trained to predict the labels that had been assigned by the teacher. So each mimic clinical document, if it's an imaging report, it would get 10 logits or predicted probabilities after transformation of each of those outcomes. And then the student model's training objective was essentially to learn to predict those numeric labels. Once that student model was trained, we again shared it with Memorial Sloan Kettering, which evaluated it on their own, privately held behind the firewall clinical documents. We used pretty standard binary classification performance metrics for evaluation, which here included the area under the receiver operating characteristic curve. We also looked at other metrics, area under the precision recall curve and best F1 score. I don't have these here for the sake of time, but I'll review the AUROCs. This is just a quick sort of table one of the cohort. So for the imaging report models, we had about 37,000 reports for about 3,200 patients from our site. And then MSK had about 24,000 reports for about 2,700 patients at their site. And you can see the breakdown of cancer types here. So these models were trained across cancer types, though we did evaluations in subgroups of cancer, which have generally shown that the models perform well across cancer types as well. And then for the oncologist note classification models, again, we had about 39,000 notes for about 3,600 patients at Dana-Farber. MSK had about 41,000 notes for about 3,600 patients. And then this is a summary figure of the AUROC metrics for the binary classification task of extracting the presence or absence of each of these outcomes along the x-axis from imaging reports. The orange bars represent the AUROCs of the teacher model when applied to the Dana-Farber test data. The blue bars represent the performance of the student model when applied to the Dana-Farber test data. And then the gray bars represented the performance of that student model when evaluated on MSK data. So pretty solid performance for this task by this metric, even for the student model, even at a second institution. And then these were the metrics for the oncologist note models. Generally similar patterns, though I think probably a bit more of a drop off in performance of the student model, at least for that progression task when shipped over to MSK. I mean, still an AUROC of 0.91, but it does look numerically lower than at Dana-Farber, sort of on the training type of data set. Nevertheless, pretty clearly, I think, robust signal at a second institution. So I then sort of tried to red team these models or interrogate them to try to understand what, if any, residual privacy risk they still posed. This was one way I tried to do it. So here, I essentially retrained the teacher model on Dana-Farber data and intentionally overfit it on the data set, since the vulnerability of a model to, in particular, that membership inference attack concern is sort of correlated with the extent to which the model is overfit in a way, since really the way those attacks work is essentially just looking for model outputs where the model is very confident. The model's going, oh, I've seen this before. The chance that this is progression is 100%. That's the type of pattern that these attacks would exploit for a classification model, at least. And here, as expected, this is over here on the left is really just showing that the model can overfit on the training data set. And when you then evaluate it on the training data set, you get the type of near perfect performance that you would expect of an overfit model on the training data set. Uh, Over here, though, when I overfit the student model on the mimic labels until it was as good as I could get it at just perfectly predicting those labels on the student data set, and then evaluated the performance of that model back on the training data set, it no longer looked as overfit, at least by this confusion matrix method. All of this is always going to be, in some sense, circumstantial evidence of privacy protection, since again, once a model is trained, there's no way, at least that I'm aware of, I'm interested if folks are aware of others, to try to say quantify the differential privacy protection retrospectively. This was another example of essentially trying to do my own membership inference attack against both the teacher and the student model. This was a type of attack that involves training shadow models, because so it assumes that you don't actually have access to all of the underlying training data, since if you did, the cat's really out of the bag anyway. It's if you have access to some data that you think kind of look like the training data. And so then you train these shadow models to try to predict the outputs of the victim model using the data that you have that kind of look similar. And you're trying to train those to predict whether the training data set split from your data can be differentiated from the non-training data once you train it. Anyway, if you get a good AUROC here, that would be a sign that your membership inference attack model has good performance and can successfully attack your victim model. Here, I wasn't really able to get good performance at this, even when trying to attack the teacher model directly, and then certainly still no for the student model outputs. But this is what I alluded to, so don't try this at home. So after doing some of this work, I read with great interest this paper called "Students Parrot Their Teachers: Distillation is Not Enough." And so this was a look at essentially how much privacy protection you get from doing what was essentially the approach we wound up implementing. And these are diagrams of the performance of the teacher model itself that's being attacked, and then the membership inference attack performance, basically modeling or illustrating the vulnerability of each individual observation in the data set to the privacy attack after distillation. So essentially, if the points are all on this straight diagonal line, then you're getting no privacy protection at all from doing the distillation exercise that we did. When you see some more of the points start to fall below the diagonal line, then you're getting at least some privacy protection from that distillation activity. And so, like, for example, this CFAR 10 data set, there was some privacy protection, but some of these others, not a ton. So doing this on its own, I think, is not enough to achieve at least formal privacy guarantees. This is another paper I read with great interest and trepidation about a somewhat different question, which was what are the residual privacy risks when a model is trained on de-identified data or even on synthetic data if those synthetic data are still sort of seeded by some truth, some real data. One of the reasons I read this with interest is I had been working on um, generating synthetic data notes, say, from sequences of real but de-identified clinical events for other use cases. We work on AI for clinical trial matching. But once I saw this, I figured, okay, that may not be enough either. And so I went back to the drawing board and I created a more fully synthetic data set. So this essentially illustrates the performance of a membership inference attack model here as measured by the AUROC at attacking models that were trained with de-identified and synthetic data, and they're still getting signals, um, uh, greater than 0.5, which would be no effective attack for this metric. So I think there's still some work to do to try to figure out how best to approach this problem. Certainly, privacy and data security are a big challenge for AI model sharing. I think we still need more research to understand a couple things, well, many things, but what are the privacy risks of even safe harbor de-identified data? So I don't know how deeply folks here have to think about HIPAA privacy rules when working with healthcare data. There's a set of specific identifiers, which once you remove them, I think it's 18 of them, name, medical record number, like license plate, IP address, data sets are considered de-identified. But then I think there's a number 19 or so that says any other information that could uniquely identify a patient is also potentially an identifier. And I worry that, at least in theory, data that have been de-identified from a safe harbor perspective with those explicit identifiers removed um, can, if used for model training, at least in theory, still be vulnerable to certain forms of attacks like these membership inference attacks, to the extent, again, that this is a realistic form of attack to even worry about because it implies you already know something about a patient. You're trying to find out more. Uh, as this is done, certainly, I think it will be helpful for privacy officers, information security folks to be able to get some practical guidance on how to think about and quantify these risks. I think the instinct often, without more quantitative guarantees, is often just to say, well, then we can't do any of it because we don't know that there's no risk. But obviously that, limits research progress also, which is also undesirable. Um, that said, I think for some use cases, probably especially classification models that already, I think, certainly have a lower risk of data leakage than a generative large language model. I think distillation, as I showed even on that figure here, can be one privacy preserving mechanism or partially privacy preserving mechanism. Um, and can be a useful tool. There's a version of this distillation approach called private aggregation of teacher ensembles, which does that distillation strategy, but trains multiple teacher models, uses them to label the student data set, uh, essentially yielding an ensemble model. So like instead of one teacher label, you get 10 teacher labels for the same mimic imaging report. You average those, you add a little noise, and now this comes with patient privacy, so with some formal differential privacy guarantees. There's also other methods for trying to do this. Differential privacy stochastic gradient descent, DPSGD, can be applied, but has some of its own challenges as well. So that said, we have made these models available in the past. as I alluded to, Memorial Sloan Kettering was able to try them out. Kaiser, some researchers at Kaiser have also explored them for tasks like looking for recurrent or progressive breast cancer or colorectal cancer in their data sets and have seen consistent performance signal for those tasks. They're not perfect, partly because they're unimodal. So they'll be able to say if a radiologist said something's getting bigger, that's different from saying this wound up being proven to be cancer later on a biopsy, but it can still yield a signal. So that's what I have. Certainly happy to hear thoughts, questions. If anyone has solved differential privacy, please let me know. I'm very interested to hear.
Well, great. Thank you very much for that talk.